Welcome to the oloavd-stanley alfi-delfi channel. Stick with me until the end of this explainer because we're going to fully master the topic at hand. Here is exactly how, as a chief engineer candidate, you must answer the critical oral exam question regarding parallel crises at sea, frequency fluctuation versus loss of excitation. Imagine you're standing right at the center of the engine room. The seas are heavy. Suddenly, alarms pierce the air. As the chief, your eyes dart across the switchboard. Recognizing the profound differences between these two deadly faults is going to determine whether you execute a controlled recovery or plunge your vessel into a catastrophic blackout. Let's take this very slowly and step by step.
To really nail this for your surveyor, we'll follow a highly structured cognitive roadmap. We've got a 6-part structure here. We'll start with the oral exam setup, look at 2 crises in 2 worlds, dive into technical causes and diagnostics, cover immediate detection and response, compare recovery procedures, and finish up with leadership and prevention. Framing your answer exactly like this demonstrates true competence.
Section 1. The oral exam setup.
So the surveyor looks you dead in the eye and poses this exact prompt. How do you handle frequency fluctuation versus loss of excitation? Now, what is truly dangerous about this specific question is the trap it's setting for you. To the untrained ear, both of these scenarios just scream electrical emergency, right? They both trigger alarms, they both risk total blackouts, and they both demand rapid engine room manning. But if you confuse a single generator's instability with a parallel generator fault, well, your actions will actually cause the exact blackout you're desperately trying to prevent.
Moving to Section 2. 2 crises, 2 worlds.
This right here fundamentally illustrates the operational divide between these 2 emergencies. First up, let's look at frequency fluctuation. Think of this as a single generator scenario. It's a prime mover, speed control problem. Because only one generator is supplying power, an unstable frequency swinging violently between 57 and 63 Hz means your entire bus bar is unstable. It's a wild ride. This is an active power or kilowatt issue. On the flip side, loss of excitation is a parallel operation fault. Picture this: you've got 2 generators already synchronized, happily sharing the load. Then, out of nowhere, one loses its magnetic field and starts drawing massive reactive power, or kVAR, from its healthy partner. The frequency? Well, it might actually stay stable at first, but your voltage and currents? Absolute chaos.
Section 3. Technical causes and diagnostics.
Now, the underlying math tells the whole story here. Frequency, which is F, equals P, the number of poles, multiplied by N, the RPM of the prime mover, all divided by 120. Because the number of poles on your machine is fixed, a wildly swinging frequency mathematically proves that N, your engine's RPM, is hunting. Your mechanical governor is failing you, and because of this, the entire ship suffers. You'll see motors running erratically, sensitive electronics tripping out, and your steering gear hunting. It affects the whole shebang.
Let's methodically break down the root causes. Frequency hunting is basically born from mechanical and fuel issues. You're looking at things like a governor actuator failure, maybe clogged fuel filters, misfiring cylinders, or even heavy rolling causing fuel slosh in the tanks. Put simply, it's a mechanical failure that's manifesting electrically. Loss of excitation, however, that is purely an electrical fault. The generator has slipped into induction mode because the DC supply to the rotor has completely collapsed. So here, you really need to diagnose the automatic voltage regulator, the AVR. You'll be looking for a rotating rectifier diode failure, a rotor earth fault, or maybe slip ring arcing.
Section 4. Immediate detection and response.
During a frequency fluctuation, your panel is going to light up like a Christmas tree with frequency high/low, overspeed, and load imbalance alarms. As chief engineer, your immediate action is to acknowledge it, get on the phone to the bridge to warn them of a potential total blackout, and aggressively start reducing non-essential loads. You are literally fighting for the survival of the plant here. But for excitation loss, your alarms are a completely different beast. High current, low power factor, reverse power, and the LOE relay. Your immediate response here is all about identification. You have to ask yourself which paralleled unit is actually the faulty one. You still need to quickly inform the bridge, of course, but the urgency shifts a bit because, remember, you have a healthy partner already online to lean on.
And that brings us to a favorite question of surveyors to test your decision-making. During those crucial first 60 seconds of chaos, can you parallel or take another generator on load? Think really carefully about your answer here.
For frequency fluctuation, absolutely not. No way. Immediate synchronization is practically impossible because the bus is wildly unstable. Your synchroscope will be spinning erratically.
Attempting to close the breaker now risks an out-of-phase closure, massive circulating currents, or even a catastrophic explosion. You have to wait for the bus to calm down. Conversely, for loss of excitation, you actually don't desperately need to take another generator on load immediately. The healthy generator is already holding the bus. Your pathway here is swift isolation. You want to open the breaker of the faulty set promptly, letting the healthy machine take the full load safely.
Section 5. Comparing recovery procedures.
For frequency fluctuation, your absolute primary mindset has to be blackout preparation. Once you've notified the bridge and got the engine room manned, you've got to immediately begin aggressive load shedding. You'll go ahead and start the standby generator, but, and this is absolutely crucial, do not synchronize it yet. Anticipate the blackout by preparing the emergency generator. Only once conditions are completely stable, or the blackout is safely cleared, can you restore the healthy main generator with full sync checks. Finally, you'll investigate the mechanical root causes in the governor or fuel system before doing your final load tests.
Now contrast that with excitation recovery. Once the bridge is notified, your top priority is a swift load transfer and isolation of the faulty breaker. You are basically surgically cutting out the sick machine while the healthy one seamlessly takes over the load. Once that healthy generator is stabilized, you can safely parallel a standby generator because, well, your bus is secure. With the ship fully powered, you can then safely investigate the AVR, perform insulation tests, and eventually re-parallel the repaired unit. Notice the huge difference here? Handled correctly, the lights never even have to go out.
Section 6. Leadership and Prevention.
A true chief engineer is defined by what happens before those alarms ever sound. To prevent frequency crises, your team has to be absolutely religious about governor calibration, pristine fuel management, and routine vibration analysis of the prime movers. To prevent excitation loss, however, your focus shifts entirely over to the electrical realm. You've got to enforce strict AVR testing protocols, meticulous maintenance of brushes and slip rings, and regular calibration of your protective relays.
Under the SOLAS and ISM codes, real leadership requires adopting the exact right mindset for the specific fault you're facing. A frequency issue requires broad, system-wide blackout preparation. An excitation issue, on the other hand, demands fast, precise electrical isolation. In both scenarios, calm communication and coordinated team training, which means running separate, distinct drills for both faults, are your ultimate tools. That's how you turn a potential disaster into demonstrated competence.
So, before you face the surveyor, ask yourself this one final question. If both alarms triggered simultaneously on a dual fault cascade, which breaker would you open first to save your ship? Thank you for your time. If you found this explainer valuable, please subscribe, like, and share it with your peers. Best of luck on your exam from oloavd-stanley, alfi-delfi.